Prof. Cheng from IMS on the stage to introduce the speaker. Prof. Cheng, please.
Very glad to see all of you here. As I was introduced, I'm Louis Chen. I'm the director of the Institute for Mathematical Sciences at NUS. And I'm very pleased to say that we have this opportunity to organize jointly with the NUS High School of this public lecture, the organizing public lecture. I'm always, I'd like to thank NUS for providing this auditorium and also for getting you people here, informing you of this public lecture. I'm always intrigued by how movies are made, how visual effects are created, and how animation is done. Now today, we are very fortunate to have a young and brilliant Singaporean, Chung Chia Yi, who has substantial experience in computer animation for movies, and who has a lot of passion for it, to come here to tell us something about visual effects, computer simulation, animation, and to tell you some of the secrets that you probably don't hear in other places. Now, Chia Yi is currently a technical director at Pixar Animation Studios. His office is based in California. He graduated from Stanford University with a bachelor and a master's degree in computer science. I don't know whether you have watched one or more of these movies, Wall-E, Up, and Toy Story 3. Now, if you have watched any of these, you'll be amazed how animation has been used in producing this movie. And you have to give credits to Chia Yi for very much involved in the production of these movies. His work is research, design, and implementation of simulation tools for these movies. So, without further ado, I'd like to invite him now to tell you the secrets of his work. The title of his talk is Numbers and Code Behind the Magic of Visual Effects.
Can everyone hear me in the back? Yeah. Okay, so good morning to all of you. Thank you for inviting me over today to give this talk. I'm very honored. So I'll just dispense with the non-important thing. So my name is Chia Yi. I'm working in the Bay Area. I'm Singaporean, and I did computer science at Stanford University. And I'm currently at Pixar Animation Studios. We're in the production of making feature films, and I've worked on these movies. Working on the next movie, which I'm not allowed to talk about. So let's get straight to the talk. Okay. So what do I do? So the term technical director doesn't really mean anything. So in life, you shouldn't worry about terms and terminology. You actually care about what the content is. So what do I actually do? I implement simulation technology for the studio. And what does that actually mean? Well, that's what the whole purpose of this talk is going to be about. There's a huge amount of technology that we employ in making feature films. And a lot of people are kind of amazed or sometimes I was shocked that we use so much technology, especially when we talk about animated movies, right? Because they think it's all a lot of art people drawing interesting images, and that is very important as well. But today I'm telling you the other 50% side of the story, which is the technical side of it. So the field of visual effects, it requires relatively large amounts of knowledge in mathematics, physics, and computer science. the amazing images that you've seen on screen, like Pirates of the Caribbean or Avatar or Last Airbender, they're all generated by computer algorithms and mathematics. That's really how it's done. And the other reason why such visual effects are possible is because of the explosion in computing power in the past 20 years. So Jurassic Park is really the first movie that defined it. You could have digital creatures on screen in a believable fashion, and that completely blew people away. After Jurassic Park, a lot of other movies came about, and that was due to the rise of computing power. And now, with these new powerful computers, we can actually employ the mathematical foundation that we have to produce these amazing images. So I'm going to walk through a bunch of real-life examples. They're mostly from WALL-E, and I'm going to sort of give you a rough idea of how it's sort of done. Go through some, at a very, very high level, of course, the algorithms that are used to produce such images. And the whole point is to be able to see behind the black box, right? That's in front of you. You don't actually understand what's behind it to produce something new, because every movie is a new challenge. So let's talk about WALL-E. So if you haven't seen WALL-E, it's fine. It's a movie about a rather bleak but funny version of the future, where human beings have sort of destroyed the planet and have fled to outer space, right? And they have thrown a lot of trash onto this planet, and it's become uninhabitable. So they've escaped in these huge spaceships and brought along with them a lot of these robots to service them. So over the course of a couple thousand years of evolution, they eventually evolve into these huge, overweight, flashy, fat things, right? It's funny, yeah. And when the director Andrew Stanton first, pitched his vision of WALL-E to everyone in the studio, we were all very excited. But at the same time, it's actually a very hard problem, because what he's actually saying is we want to have animated, deforming fat creatures in the movie. And animating a deformable object is actually a very, very hard problem. So if you think of it, even for quote unquote, a simple object like a piece of jelly, how would you animate a piece of jelly? There's a lot of interesting, very subtle secondary motion jiggle that's involved when you move a piece of jelly from one place of the table to another, right? If you push your finger down the jelly, it's going to deform. And then when you lift your finger up, the surface is going to bounce back and then oscillate about. So that's another interesting, wave-like secondary motion that's involved in just animating a simple piece of jelly. Now, it turns out that human flesh, it's somewhat like jelly. It's not completely like jelly, but it shares somewhat the same properties. So if you push your finger on a piece of your own flesh, and you let it go, your skin is going to bounce back. It's going to try to retain its rest shape and preserve volume. And then if you push your arm into your belly, it's going to it won't intersect your belly. It's going to push your belly in, right? So there's some kind of collision response involved in that. It won't directly intersect your belly. So all these interesting phenomena have to be modeled accurately on a computer in order to make a believable world WALL-E. If you don't do that, your animation is going to become very, very stiff, and it just doesn't make for a good movie. So here is the dark actually. Here is, can we brighten up the projector image? But anyway, here's the image that we're trying to work with. This is the final rendering, final shot of the fat captain on WALL-E. And you notice that there's a bunch of very interesting shapes in this image. So you have a curvy arm here resting on the belly hook. You can see it's really dark, but you can see the bulge coming up. So you have to model that. And then when the captain actually moves, the flesh is hopefully going to jiggle about like a very disgusting fat man, right? And we have to do that as well. So let's start with the basics. So how do you actually represent characters on a computer? at a very, very basic level. So we need a set of points, because, go back to this image here, we need a set of points to define points on the surface of this character. A set of points in 3 space, right? So x, y, and z. And in addition to the points, you need to be able to define the topology of the surface, that is, the relationship between those points, because the surface is not just a single point, it's composed of many, many points, and we need a way to represent, how the surface is going to be drawn on the computer. So we need a set of points, and you need to say which points are connected to which. Here's the example, like a dolphin, a simple dolphin made out of points and with topology. In this case, the shape we're using to represent a dolphin is a triangle, right? So this is what I'm talking about. Nothing wrong with this image. In fact, this is how you would typically represent a shape on a computer with a triangulated surface. There's just one problem. So in the real world, so a triangle is a flat object, right? In the real world, we need some kind of volumetric representation of the object. If it's a flat surface, we're going to have a really difficult time simulating it as flesh, because flesh is volume, jelly is volume. So a triangle isn't going to work. So we need another basic primitive, just like the same analogy, but for volumes instead of for a surface. So what's the most basic primitive we can think of to define a volumetric object in 3 space? And it turns out that it's called a tetrahedron, sorry. So it's the equivalent of a triangle but for volumes. It's sort of like a pyramid-type shape. And what we're going to do is we're going to basically fit these simple atomic blocks, these tetrahedra, into the captain, into the fat object. So imagine the entire object, instead of getting just now I'll show you the image. This dolphin is made out of completely of triangles. Now we're going to make this dolphin up completely, we're going to make it up completely out of tetrahedron. Let me just show you the image. So this is an image from, I believe, a paper from Berkeley. I could be wrong, but the whole point is that there's a cutout, cross-sectional cutout of the image, and you can see that there's tetrahedra, these tiny tetrahedra inside this object. See that? So we're going to do the same thing with the captain, and I'm going to talk about how we do it. So there are a couple of problems here, right? How do you actually fit tetrahedra into a complex shape like this? And the idea one idea is to do it like sculpting. So you take a huge block, like a rectangular block, regular rectangular block composed of tetrahedra, and then you take your virtual chisel and you start sculpting away. So you start, tossing away tetrahedra that don't belong to the actual volume of the object, in this case the captain. So you slowly start sculpting away the shape until you get the shape of the captain. And that's sort of what we're doing. So we're going to overlay over the captain a 3D volumetric grid. Okay, and the grid is composed entirely of tetrahedra. Okay, so imagine a huge volumetric rectangular grid now composed of tetrahedra that bounds the volume of the captain. And then we're going to slowly chip away, go through each tetrahedra in the rectangular grid, and we're going to slowly chip away the tetrahedra that don't belong within the volume of the captain. So how do we do that? Well, it's not, a couple of issues, right? One issue is that we need to know if, given a tetrahedra in the rectangular grid, does it actually belong within the volume of the fat captain or not, before we decide whether we're going to cull that tetrahedra away. So that's the first question we need to answer. And we're going to come back to this image a lot more later, but this is basically one of the programs I wrote for WALL-E. And this is a 3-dimensional cutout of the captain. You can see all these, unfortunately it's still a little dark, but these wireframes here, they represent the tetrahedra of the captain. This is a cross-sectional cutout. And you can see that he's composed entirely of these basic building blocks. So one way to do it, to determine if a point is within the volume of the captain or not, is to use something called a sign distance function. And the idea again is pretty simple. The whole point is say, okay, given a point in free space, right? This function is going to return you the distance to the closest point on the surface. If the value is greater than 0, we know that a point is outside the volume of the captain. If the value is less than 0, it's inside. If the volume is equal to 0, then we know that we're directly on the surface of the captain. We call that the interface. It's signed because there's greater. If it's greater than 0 or less than 0. That's why it's called sign distance function. So the idea is that we're going to generate a sign distance function for this three-dimensional object, which is the captain. And how do we generate a sign distance function? Well, I'm not going to go into details with this, but there are lots of algorithms to do it. One of them is called the Marching Cubes algorithm, or Marching Tetrahedra. And it will actually basically generate a nice sign distance field for you. And then you'll be able to use that to accomplish what we're going to do next. So the sign distance function, I can give you a really simple example, like equation of a circle, right? It could be something like, let me try to write it down. Actually no, because the projection's not really working. But imagine a circle, and x squared plus y squared equals some radius. So if you have a circle and you put in, you can basically find the distance to the surface, the boundaries of the circle from that equation, and then the distance to the boundary is going to be the sign distance. So you know that whether you're inside the circle or outside the circle, and if you actually put in numbers that satisfy that equation, then you're directly on the circle itself, which is the interface. So we generate the sign distance function for the character using Marching cubes, and then once we have that, we can go through every single tetrahedra. Now, a tetrahedra has a set of points in it. So for each tetrahedra, we basically test it using the sign distance function, and we ask the question: is this piece of tetrahedra with the following points inside or outside the captain for each of the points, right? And we call away the tetrahedra that do not belong to the interior of the captain. So once you've done that, you can have a very blocky-looking sort of captain-like character. It doesn't exactly follow the boundary of the surface well, but it's sort of a very blocky-looking object. So you have an unrefined tetrahedralized volume of the captain. The next step you want to do is, using the same sign distance function, you can actually get the normal to the closest point on the surface. So we can actually push those surface tetrahedra into the captain to make it align more closely with the boundaries of the outline of the captain. And if you do that, the end result is exactly like this. So this is the final result after all the steps I've talked to you about. And with this tetrahedralized mesh, you can finally start simulation, because you now have a three-dimensional volumetric representation of a character for your feature film that we can use for simulation, to simulate Flash. So now we have the character, and it's composed of a set of tetrahedra. So we need to make it actually respond to real-world physics. Couple of requirements, right? The character has to stretch, has to compress, but at the same time, it should also try to retain volume. And when this flashy character hits something else, like an external collision object or itself, like if it takes its hand and hits its face, there should be some kind of collision response with itself and other objects. So it's a pretty tricky problem. And one of the techniques we can use is called the finite volume method. It's a technique that's very often used in engineering to model the stress and strain relationships on bridges, airplane wings, that sort of thing. And you can use it to actually model the stress and strain relationship on flesh. The interesting thing about finite volume or finite elements is that you can basically measure the physical properties of almost any real material like wood or metal. If you measure it accurately enough, you can take those parameters and put it into your algorithm and run a simulation, and it will actually behave sort of like wood or like metal. So let me show you a video to illustrate what I'm talking about. So this is a video. We're making a Buddha statue that's actually, we're giving it a property sort of like rubber. So it's very, squishy. And we're going to throw it through these two gears. It's going to compress. And then at the end, when it reaches the end of it, when it's outside the two gears, it's actually going to retain volume, so it's going to bounce back to its original shape. So yeah, it's actually really difficult to do. So notice how it retains volume as it falls through the gears. You can play that again. And at every time step, basically every time frame, the computer is doing a lot of calculations to make this actually happen. This is basically done with the finite volume method, which I just talked about. And we're going to use this exact same technique for the captain. So keep that in mind. So, okay. The other problem is that the captain is not just going to be a big floppy character, right? Human beings have an internal bone structure in them, and we need something like a stiff interior to represent the bone structure of a human being. But the outer exterior should be flesh, should be sort of floppy. So we want something like a fish, like this floppy fish, for instance, where there's a stiff internal bone structure to represent its interior skeleton, but on the outside, it's a floppy piece of flesh. I have a video to show you again. Let's take a look. Again, this is done with the finite volume method. So this is completely simulated on a computer. There's no human animation input involved in this. This is fully simulated on a machine with the finite volume method, and also putting in parameters to stiffen up the interior of the fish so that it has some kind of bony structure. Okay, so let's say we have that. If we take the character now as it is, composed of tetrahedra with a stiff interior like bone structure and using the finite volume method, if you drop it right now, it's going to behave like a ragdoll. It's going to drop, flop around and do nothing, like a doll, because there's no external motion to drive it. So we need to actually make the characters respond to human animated input. Basically what it means is that we need human beings to go in and sort of act out the general motions of the character, and we want the character to follow the motions of the acting, but at the same time it has to have the very nice secondary motion, the sliding effect, the belly jiggle, and the floppy motion as well. So we want all of that. So what we want to do is what we're saying is that we want the simulation to target the desired human animation. That's essentially what we're trying to do here. One way to do it is use, springs. So the springs, as in the springs we use you learn in physics. Why do you use springs? Well, I'll go into that soon. But remember the basic spring equation in physics of Hooke's law. So force is proportional to the negative of the displacement, where k is the spring constant. So the idea is that if you attach, imagine that we have our simulated mesh, right? And it drops like a ragdoll. If you attach a tiny spring between every single particle on the simulated mesh and a particle that's driven by animation, we're going to have, what happens is we're going to have the simulated mesh's particles follow the animated particles. So they're going to be pulled along. It's going to be like a piece of glue that's stuck to every single point on the simulated mesh, and you're going to be pulling these points around, and it's going to drive the simulation. And that makes, it's pretty cool stuff. And I'm going to show you some videos soon. So what that means is that you're going to have the animator come in, animate some basic poses, and then take the points on those animated poses put them into our simulation and make them drive our simulation. And so if you take a look at the basic spring equation again, if you hopefully remember that, the force is negative k times x, right? And velocity is the derivative of the force with respect to time, right? So given the force on the spring, we have to calculate the velocity. And then once we have that, we have to calculate the position, which is the derivative of the rate of change of velocity with respect to time, plus the old position. This is physics. And if you do the following steps, it's called explicit Euler time stepping, because you're basically integrating over time. You're saying that each step in time, what's my force, what's my velocity, and then what's my final position. And then you move on to the next time step. And you ask the computer the same question again. What's my force, what's my velocity, what's my new position? And you do this thousands and thousands and thousands of times for every single particle, and over the length of time that we're animating or simulating against. If you do that, then you get a full-on spring simulation. There's actually a lot of problems with explicit Euler time stepping. One of them is that it's actually unstable for large time steps. Because if you remember from basic calculus, this dt here is actually a really, really small number. But in this case, because we're doing it on a computer, and everything on a computer has to be discrete. So when you pick up dt, it has to be of some value. If you pick a dt which is too large, your simulation, the steps you've done here, the simulation is going to blow up, and you're not going to get very good results. So the illustration I have here is here. So if you actually were to solve the equation like on a pen and paper, you're going to have a correct path over here. Whereas if you were to run the explicit Euler time stepping, you're going to get something that diverges from your intended path. So that's bad. So the solution is not to use explicit Euler. There's a lot more sophisticated methods that we can employ to solve this problem. It's a pretty large field. All I'm going to say is that we employ a fully implicit method to solve the spring equation. And that means that we can take really large time steps. It's very stable. That means the animator can act out the character in all kinds of different poses, and we still get good quality results that don't diverge from his intended output. So let me show you some videos actually. The first video I'm going to show is it's a test video of the captain. Let me loop it again. So here is the captain. The animated those poses and him like jumping around, doing that funny stance, and then we put it into our simulation system, and it's driven by springs, which drives the tetrahedralized volume, and then it does all that cool floppy sliding motion on the belly. So this is the exact same system but described as a video. So this is exactly what I told you. Now, if you actually take that and you tweak the parameters slightly differently, you're going to get different looks. Because with finite volume, we can get different looks for to achieve different properties for the material. So this is with a test with different parameter inputs. And in this case, the material is a lot floatier because we've tweaked the input parameters differently. But notice how the belly jiggles about and reacts to the motion of the captain. As he stomps his foot on the ground, there's a shock wave coming back, it hits the belly, and all sorts of interesting behavior happens. See, he stomps his foot, yeah. And this is really difficult to do if you didn't have simulation, because the animator will be forced to animate all that secondary floppy motion and the collision response with the belly and all that. It's very, very difficult for a human being to actually do manually. There's too much detail involved. So for these kinds of problems, you want to leave it to a computer because that's what they're designed for. It's easier for them to do it. And here is the final shot in the movie. Let me try to find it. So, it's a little dark, but basically the bulges on the captain's body, they're also, you get them for free through the simulation because the flesh, the fat, basically rolls on top of the belly and intersects the bottom of the belly. So because of real physics, we're simulating physics here. So it actually pushes the top of the belly upwards to get a nice bulge shape, which is again pretty difficult to do if you wanted to sculpt it manually because there's a lot of work involved. Okay, so next I'm going to talk about what we do next from here. We have a single character. We have a character that responds to animation input. However, the director comes along and says, "Oh, for the final shot of the movie, we need to simulate a lot of characters, not just one character. We need to drop a lot of these fat people from one side of the ship to another. So they're going to roll over each other and do all kinds of interesting stuff. And again, it's too much work for a single human animator to animate. So we have to do it with computer simulation. So now we're going to do the same thing, but with groups of characters. Okay? And the idea is that we just do exactly what we did before. We get animators to go in and animate a library of poses. So they have like different motions, people flailing about, kicking about, falling over, basic motions. We save that into like a database somewhere. So we have a set of animated poses done by human animators. And then we take those set of motions and we apply it to different characters in the game. And then we turn on gravity, we turn on collision objects, and so on, and then we run the simulation. And then I'll show you a bunch of videos. But before that, here is the rough outline of what happens. So we get people to animate some basic poses manually, and then we input them into the different characters in the movie. Say you have 50 characters or something. They start acting out their basic motions. We throw them into the simulation system. We turn on gravity, ground, and other external colliders, and we run the simulation over some period of time, and you get the results. Here are some results. Let me see if I can find it. Okay, so here's an initial test. So we have a lot of characters. So we have a lot of characters falling from one side of the ship to another. So everything here is fully simulated, other than basic motions, of course. When we drop them under the influence of gravity, this is what you get. You notice that this guy is rolling over, and you get that almost for free from the simulation because he's colliding with the bridge, and so he's rolling over because of angular momentum, all that kind of stuff. Here is another video. This is from the final shot in the movie itself, and okay, again, every character here is simulated. This guy is rolling over. That's kind of funny. This guy's driving onto a chair. These people are sliding over. And the chairs themselves are also responding to the way characters collide with them. So there's a collision response associated with that. So this shot itself would be very, very difficult if you wanted to do this manually with just human input. You have to have some sort of simulation system in order to pull off a shot like this. There's a lot of shots in a movie that are on the scale. In order to sort of scale upwards, if you wanted to animate hundreds and hundreds of characters, you need a smarter way of doing it instead of just having raw human input. So finally, I'm going to just talk about something in general. which is what other things in visual effects we can do. Before I go into this slide, I'm going to show you a couple more videos. So this is from Up. So from Up, this guy here, Russell, there's these dangly items on the back of his backpack. And those look simple, but they were actually simulated on a computer, because it's actually, again, very difficult to animate dangly items manually. So we actually ran a rigid body, an articulated rigid body simulation on Russell's backpack. And articulated rigid body means that you have a rigid body that is constrained to some point. So it can rotate about, but it's not able to leave that point, which is perfect for a dangly item, right? Because you have an item that is physically sort of attached to some other constraint point that you want to follow. But it should dangle about and do all kinds of interesting behavior. So if I play it, that's what you get. And if you watch Up, the backpack was all that subtle dangly bits going on that was done in the simulation, so that the animator could focus on actually emoting the character and doing the things that they like, making the characters laugh and cry, and not worry about animating these boring bits of equipment. So the other couple of things that you can do with simulation, and let me get back to the slide. I'll show you the video later on. But so what I want to say is that visual effects doesn't actually require like a very expensive studio to do. You can actually do this from your home, and that's basically how I started. What you do need though is you do need some understanding of mathematics and physics. You do need to know some computer science. You need to know the basic algorithms and all that. You need to have a lot of determination, hard work, and you need, lastly, a sense of imagination. And luckily for you, today the internet is probably your friend, right? Almost everything can be found on the internet. A lot of these materials are actually available for free. There's kind of lessons online you can watch for free. And so it's not as inaccessible as before. The barrier to entry is a lot lower than maybe in the past, like 10 years or something. In addition to that, the cost of hardware has also gone down dramatically. So any basic laptop now, I can guarantee you, any laptop you can buy for $200 or even $100 is more than powerful enough to run a basic physics or a physics simulation. Just because of the explosion in computing power. Of course, if you want to do something more complicated, you need more powerful computers. But I'm saying that most of it is more than enough to get started. The software is also free. So if you have a Mac, you get a C++ compiler for free. If you have a PC, you can go to Microsoft and download a free version of Visual Studio. If you have Linux, it's also free. So the cost, in terms of the barrier to entry, in terms of cost, is also a lot lower. So in that sense, you're, I think, pretty lucky. And now I'm going to sort of, let me see if I can run this demo for you. So this is a fluids demo that was written by a professor called Jos Stam. He used to be a professor, now he's actually working at Alias, which is the company that made Maya. And he wrote this simple 2D smoke fluids demo a couple of years ago. And what's interesting about this is that it basically runs on my laptop machine in real time, just to illustrate to you how far we've come in terms of computing power. So this is a 2D Navier-Stokes, incompressible Navier-Stokes simulation. We're going to scatter some smoke values, density values on the screen. I'm going to look that. And it's in real time. That's a great thing. So let me start it again. And the point is, any machine today can run this simulation. You don't need any, super powerful piece of hardware. This can run on any desktop at home. So what you really need is the knowledge to actually utilize this hardware. You don't need a lot of money to buy very expensive hardware. So if you take this demo and you sort of take it to the next level, and a lot of work, of course, you get something like this. So this is a 3D fluid simulation that I'm actually working on this problem right now at Pixar because we're simulating bubbles for the next movie. And we're using this exact same technique as described in this video. And you can simulate some pretty amazing things on the computer today. So you get all that nice bubbles breaking the surface and all that. And if you watched, Pirates of the Caribbean or Star Wars, any movie with a ton of explosions, Transformers, all of them actually a lot of them use the same algorithms described in this paper. They can all trace it back to this and other related papers. Let me show you another video. So in this case, we're going to actually shoot sort of very dense fluid into the scene, into water, and then we're going to drop a ball of fire on top of it. It's going to catch on fire. This is full-on simulation. We're solving for incompressible flow, basically the Navier-Stokes equations, over different phases, different fluid phases. So there's a phase for air, there's a phase for oil, there's a phase for water, and it's all coming together nicely. And this is all, centuries and centuries of mathematics, physics, and a couple of years of computer science put together. We can do this now on a machine, and it's really amazing. This is how all the explosions, fire effects, fluid effects, whatever, are done on the big screen. They're all using the same technique. So finally, and just one more video to show you. You can also drop objects that follow each other. And that was actually used on the wall. And with that, that's the end of my talk. Thank you very much.
Testing. Thank you, Jai, for your fascinating talk, telling us all those wonderful simulations. Okay, I'm sure you will be happy to answer questions. So, Mr. Chong is happy to answer any question. Any questions from you? No question? You have another chance. You have to seize this opportunity to ask questions. What do you want to know? Okay, what do you want to know? You want to...
Will you be able to simulate a car crash?
Oh yeah, actually, that's what they do in Transformers. It's all full-on rigid body simulation.
Yeah. Okay.
One more there.
Hello? Right, sorry, I'm Shansi from M10306. Can I ask about the physics in the physics slide? Involving calculus?
Yeah, what about it?
Can you hold? Thank you. Can you please elaborate? Thank you.
It's really all in your physics textbook, actually. you get the force.
You mean velocity and force?
Interaction between different objects. So if you just wanted to animate a set of chairs falling on top of each other, that's relatively easy. If you wanted to animate a chair that hits a piece of jelly and interact with a piece of jelly, that's difficult. So the interaction between objects of two different material properties is a relatively difficult problem.
Okay.
Any more questions? Well, if there are no more questions, I hope that you learn something here, and next time when you go and see a movie, first of all, you hope you appreciate how much mathematics and physics and computer science is put into those effects, the visual effects, those animations that you see. Okay? One more question? Did raise anyone else question? Right? Okay.
I just want to ask about the plot of Wall-E. Because I think that because I've watched the movie Wall-E, I think that some part of the movie actually is taking reference from the 2001 Space Odyssey. Is that correct?
Yeah, that's actually exactly correct. So Hugh Stanton, the director, is a huge fan of Stanley Kubrick, and a lot of the scenes were influenced by 2001 Space Odyssey. You're right.
Okay, thanks.
So I have one question to ask. Okay, so as a computer scientist in an animation movie, do you have difficulty working with artists or with the director? Would there be a problem whereby the director asks for something but you know it cannot be done with current technology?
Yeah, actually, I was hoping someone asked that. The answer is yes. So oftentimes we have to push back. For example, on Monsters Inc., the director wanted to make monsters with long hair, and they had issues with that. They eventually figured out how to do that. Then they wanted the hair to go on fire, and then that was difficult. So the technical team pushed back on that idea, and so we didn't have monsters that caught fire on Monsters Inc. And it happens all the time in movies. So the director always has a ton of ideas, and he's going to present it to everyone in the company, and then the technical team comes in and then tells you which ones are not possible. And then we implement the ones that are possible.
Well, it's time for us to thank the speaker again for giving us a glimpse into the world of animation. Stay up there. So as a token of appreciation for coming all the way here from California to give us this talk, for you,